For our first example, we consider a solid insulating sphere of radius a and charge q that is uniformly distributed throughout the volume of the sphere. We've chosen an insulator because in our simple model of an insulator, charges cannot move. We can specify the charge distribution and it will remain fixed. Charge distributions on conductors are more complicated and we will delay discussing them for a few slides. We want to determine the electric field E from Gauss's law. In this case, the charge distribution possesses spherical symmetry. That is, the charge distribution itself is only a function of r, the distance from the center of the insulator. Since the charge distribution is spherically symmetric, the electric field produced by this charge distribution must also be spherically symmetric. Its magnitude can only depend on the distance from the center of the insulator, and its direction must be radial. To calculate the value of the electric field at a distance r from the center of the sphere, we choose our Gaussian surface to be a concentric spherical shell with radius r. We know the direction of the field at all points on this Gaussian surface must be radial, and therefore perpendicular to the surface. Consequently, the scalar product, E dot dA, just becomes the simple product, E times dA. Furthermore, since all points on the Gaussian surface are equidistant from the origin, we know the magnitude of the electric field at all points on this surface must be the same. Hence, the electric field at the surface is a constant and can be taken outside the integral. Gauss's law then becomes the electric field times the integral over the Gaussian surface of dA is equal to the charge enclosed by the Gaussian surface divided by epsilon naught. The integral of dA is just the area of the Gaussian surface. Therefore, the left-hand side of Gauss's law simply reduces to the product of the value of the surface area of the sphere and the value of the electric field at a distance equal to the radius of that sphere. We'll first determine the electric field outside the insulator, i.e. r greater than a. For all such values of r, the charge enclosed by the Gaussian surface is just the total charge of the insulator. Therefore, we obtain the result that the electric field is proportional to the total charge of the insulator and inversely proportional to the distance from the center of the insulator. In fact, we see that the electric field E at a distance r from the center of the insulator is identical to that produced by a point charge Q located at the center of the insulator. We'll now move on to determine the field inside the insulator.